Hello everyone. In this video we are going to talk about PCA on images particularly. We will see how much useful PCA is on images. So as you know, PCA stands for Principal Component Analysis. So before continuing with this video, I would highly recommend you to understand what exactly is PCA, how to apply it on a sklearn, what exactly is the theory behind it. I have in detail explained it in one of my previous videos. You can easily check that out. So having known what exactly is PCA, in short it basically helps us in reducing the dimensions of our data sets. That is, we can reduce the number of features. Suppose I had told you already, suppose you have a data set where you have basically length, breadth, area and price of the house. Now within our area this length and breadth is hidden, so this area, it can be directly correlated with the this length and breadth, and hence we can also say that area is directly proportional to price of the house. So we can easily remove the length and breadth columns, or we can even remove the area column. So in this way the dimension of a data set is reduced. I had also explained with a clear example of how if the correlation score is high, or if data are highly correlated with each other, then we can apply PCA by reducing them to higher dimensions, to lower dimensions. So 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 what if we talk of images? Now images are basically 3D matrix. So it is a numpy array basically. So length and breadth are the two dimensions, and the third dimension is for RGB values. Now if we consider each pixel as a feature, then then we try to manipulate our image, we will see that images have a huge number of features. This is because even a small image of 28 cross 28 pixels will have 784 features to deal with. 28 pixels, the image will be so small, but still there are 784 features to deal with that small image. So the number of features is very high, so we need to reduce the features. Using PCA we can easily do that. Or also we'll see that there are a lot of covariance in an image. When we look at an image, it is easy to understand that if we have the values for one pixel, that the pixels in the vicinity of P will generally have similar values. Why is it so? Because you imagine your photograph in a photograph picture. If you see that image, suppose in one portion of the image your shirt is red color or maybe multicolored, but if you consider one pixel, the vicinity of that pixel, the pixels which are in the vicinity of that pixels will have very similar features, will have very similar color. So there is a lot of covariance in that image. So PCA would be a more it will be really helpful in case of images. So we will take an example of a database here, dataset, and we will just manipulate that, and we can see how we can reduce the dimension of images using PCA. So we first import the necessary libraries. From sklearn we import datasets and import matplotlib.pyplot, as well as from sklearn.decomposition we import PCA. Now we make an object handle. Basically we datasets dot fetch Olivetti faces. So this is a dataset known as Olivetti dataset. So it has a number of faces. So it has keys. Let's see what are the keys. There are data, images, target and description. If we see the shape of the numpy array of data, we will find 400 by 4096, and if we see the shape of the numpy array of images, we will find it to be 400 by 64 by 64. So here it is a 2D list, here it is a 3D list. So what we see that data is gonna contains only flattened images. So these images is a 3D matrix I told you, and this data contains flattened images. This means that one dimension is already reduced in this data. Now let us plot in these images. if we plot this 64 images using this code, we will get some data like this. And now we will create our PCA object and apply PCA. So you don't need to worry about this code of plotting. You can search the website for it. You can go for the matplotlib documentation, or you can easily Google it to understand if you are interested in how to plot. So I am basically in PLT, in my matplotlib I am shows help in showing an image, in adding a subplot, what are the arguments necessary, you can easily find out. So this code is not much important, it is just for showing you the output. So if you are interested, you can go ahead and check it out. We will also create PCA object and apply PCA. So we just create an object of data.target. These things I have multiple times showed you how to extract the x and y values. We have to do this data.target, and also this PCA we just fit like any other machine learning algorithm. We simply fit this PCA and we find out what are the PCA components. We can easily see that this has been flattened, it has dimensions similar to what our data had. Yeah, what our data had, it has dimensions similar to that. Hope you can understand this concept. And now we will decide what is the value of k. So we need to give the value of k on the amount of variance we want to retain. So basically we are now going into a lower dimensions. Now in order to go to some lower dimensions, how many features we will keep and how many features we will ignore. So in PCA, during my PCA video, I have clearly explained you that first we create some eigenvectors of all the rows, then we select the top k eigenvectors, the top k eigenvalues of those lists. So of what list we will basically create a vector of our all of our features, and then each of those vectors we will convert to eigenvalues, and when we select the top k eigenvalues from that list, so what will be that value of k. So basically out of 4096 we will be requiring to keep only 123 component if we want to maintain a 95% variance. So with 95 0.9 you can easily see this, what is explained variance ratio. You can search, or I have also explained it in my previous videos. So while current sum, to keep our variance within 95% in our range, so we will lose only 5% of information. We will lose only 5% of information if we keep just 123 features out of 4096. So we got rid of so many features, and now we have such a small data set as compared to our previous data set. Now our data manipulation will be much easier through this. So yeah, that's a good thing. Now we can also reproduce this image using the reverse transform. Using the inverse transform we can also reshape it, and then we can just plot it again. So this will not be exactly same as our original data, but definitely it will lose some of our data, but it will look very similar. Now what are eigenfaces? So eigenfaces is basically a method that is useful for face recognition and detection by determining the variance of faces. So we found out that only 123 features are required in order to maintain uh, basically 95% variance. So we will plot only those 123 features. This time we are plotting only those 123 features. So we reshape the image like this and we just plot this. So now you see we have these eigenfaces, but the interesting thing to note here is that the data doesn't look random. These components have some meaning attached to them. Each component seems to focus some particular feature of a person's face. So basically each face, you see somewhere the lips and the nose are very much prominent, and in other pictures they are not prominent, and other parts of the face are prominent. So in this way, suppose we have a picture of a criminal and we want to detect that criminal from a very, suppose the picture is really small and like only the face can be seen from a large distance, it is unrecognizable, but suppose the criminal, you suspect someone to be your criminal and you also have that face, so you can just match the eigenfaces of those two and see how much they are similar in numerical values. So this stands the base of such kind of detection of eigenfaces. So yeah, that's all from this video. In the next video we will probably be starting with natural language processing. Till then, thanks a lot.